Alright, today we're going to talk about hydroboration, oxidation of alkenes. Alright, initially what I want y'all to notice is that we have a BH3 and THF. When you see this combination followed by a peroxide like H2O2 and a base, now you could also have additionally water with it, for example, but that's not completely necessary in this situation. That will show you that it's going to lead to an oxidation reaction, essentially. So what's going to happen is you're going to add the BH2 to the molecule. So you'll have your carbons, and that will give you your BH2. However, you don't stop there. Another thing I want you to notice is now it's an alkane. But that's just the first half of the reaction. Second half will eliminate the BH2 and replace it with an alcohol or an OH. Now, this point I want you to notice that this is actually an H and this is also a hydrogen. Does not add any methyl groups, just hydrogens in order to make it an alkane and neutral. But another thing I want you to notice is that it's anti-Markovnikov. But you cannot tell with this problem over here, which is why I want to show you with this cyclopentene over here. Essentially, you would do the exact same thing. However, we can skip a step and go directly into the alcohol. Now, between these two groups, instead of going here as you've been taught, usually in Markovnikov addition, you would actually put the OH in the less substituted carbon, which would lead to an anti-Markovnikov addition of OH. Now we're going to look at the same thing, hydroboration, but now for alkynes, triple bonded ones, specifically terminal alkynes. Now, what's going to happen is, for this one right here, you have your you have your alkyne right here, and you're going to borate this with SiA2BH followed by NaOH and H2O2. Now, what's immediately going to happen is, just like with alkenes, it's going to go down one. And so for an alkene, it would go to an alkane, but from alkyne, it's going to go down to an alkene. So same thing here, and now you add your OH. However, you cannot have an alcohol and the double bond here at the same time, because this is known as an enol. And enols are not very stable. Instead, it's immediately going to turn into an aldehyde. So immediately, it's going to turn into a double bonded oxygen with the hydrogen coming out of it there. So this would be your answer. And it only works if it's terminal. If it's internal, it would turn into a ketone. So let's focus on this one here. Let's do another example. So now we have the same thing, but with a problem like this. So first thing let's do is let's simply redraw it into its enol form. Now I'm not certain I drew that correctly, but regardless, let's continue. This is your enol, your double bond connected to your OH, your alcohol. Next, it's immediately going to convert into an aldehyde. Now, you don't technically have to show the presence of the H right here. You could just leave it blank and it would already be known that there's going to be an invisible hydrogen coming from here. So it's very similar to the hydroboration of alkenes, except you have to make sure it ends stable also. If it's terminal alkyne, it's going to turn into an aldehyde. If it's internal, it will turn into a ketone.